Hello students, welcome to my channel. Third part of named reactions in organic chemistry. In this video, we can discuss about Rosenmund Reduction, Clemmensen Reduction, Kishner Reduction, Stiffen Reaction and Etard Reaction. Before going to the topic, please subscribe my channel. Press the bell icon for notifications. Like, share among your friends and comment. In Rosenmund reduction, acid chlorides are converted into aldehydes by employing hydrogen gas over palladium poisoned by barium sulfate. Due to the high reactivity of hydrogen gas, it readily initiates a substitution in the acyl chloride, forming HCl and the required aldehyde. The mechanism of Rosenmund reduction consists of three steps. In the first step, hydrogen gas is passed through acyl chloride, resulting in the formation of an aldehyde and hydrochloric acid. In the second step, the resulting aldehyde form undergo another reaction with the palladium over barium sulfate. This leads to the formation of alcohol, which further generates an alkene. In step 3, the Rosenmund catalyst is poisoned to stop further reduction once the desired product is obtained. A variety of poison can be employed for this process. An example for the method to totally deactivate the palladium over barium sulfate catalyst. The three-step Rosenmund reduction mechanism can be employed for the catalytic hydrogenation of acid chlorides to enable the formation of aldehydes. A few of the side products of this process can be avoided if the reaction is conducted in anhydrous solvents. The other reaction is Clemmensen Reduction. It is a reaction that is used to reduce aldehydes or ketone to alkanes using hydrochloric acid and zinc amalgam. This reaction is particularly effective in aryl alkyl ketones reduction formed in Friedel-Crafts acylation that we can discuss later. The reaction is more effective in reduction of cyclic ketones or aliphatic and zinc metal. See, the equations are given here. Here there are two mechanisms. One is carbanionic mechanism. Carbanionic mechanism of reaction shows that the zinc attack directly to the protonated carbon. And the second one is carbenoid mechanism. While the carbenoid mechanism is a radical process and reduces the happenings on zinc metal surface, the reduction takes place at the surface of the zinc catalyst. In this reaction, alcohols are not postulated as intermediate because subjection of the corresponding alcohol to the same reaction condition does not lead to alkane. See, that equation is shown in this slide. The underlying substance must not react to acidic condition. The acid-sensitive base substance react in the Wolff-Kishner reduction that has strong base if it is milder than it is Mozingo reduction. The reaction is not for the substances that are sensitive to acids. The heterogeneous nature makes the mechanism remains obscure in spite of its antiquity, and the studies on mechanism are difficult. There are only a few studies on the particular reaction proposed, like possibly zinc carbenoids and organozinc intermediates. The next reduction is Wolff-Kishner reduction. Is a reduction of carbonyl compound to hydrocarbons by heating them with hydrazine, hydrate and a base. In this process, the carbonyl group gets converted to CH2 group via C double bond N, NH2, and nitrogen gas evolves out. So the reaction is basically converting carbonyl groups to methylene groups. To drive out the nitrogen gas, which is a side product of the reaction, it's necessary to use a high boiling point solvent like ethylene glycol. This is a reduction for aldehydes and ketones. Other reducible groups such as carbon-carbon double bonds and nitro groups usually remain unaffected under the conditions of this reaction. The first procedure of the reduction is to heat the carbonyl compound with hydrazine, hydrate and sodium ethoxide in a sealed tube at 180 degrees Celsius. See, the equation is given. There are 5 steps in Wolff-Kishner reduction. In the first step, the aldehyde or ketone is subjected to hydrazine. This yield the hydrazone required for the process. See here the reaction of aldehyde with the hydrazine and form hydrazones. In step 2, the terminal nitrogen atom is deprotonated and it proceeds to form a double bond with the neighboring nitrogen atom. The released proton attaches itself to the hydroxide ion from the basic environment to form water. In the third step, oxygen is more electron withdrawing than carbon. The carbon is protonated by the water molecule. In the fourth step, terminal nitrogen is deprotonated again, this time forming a triple bond with its neighboring nitrogen atom. This results in the formation of a carbanion where the two triple bonded nitrogens are released as nitrogen gas. Similar to step 2, the ejected proton forms water along with the basic environment. In the fifth step, similar to step 3 of Wolff-Kishner reduction mechanism, the carbon is protonated by water, resulting in the formation of the desired hydrocarbon product as shown in this equation. Thus, the aldehyde or ketone is converted to an alkane. The rate determining step of this reaction is the bond formation of the terminal carbon with hydrogen, that is in the hydrazone anion. The carbon-hydrogen bond formation is helped by mildly electron-withdrawing substituents. Highly electron-withdrawing substituents decrease the negative charge of the terminal nitrogen, making it difficult to break the NH bond. Next reaction is Stiffen reaction. The reaction describes the preparation of aldehydes from nitriles with the help of stannous chloride and hydrochloric acid and the quenching of the resulting iminium salt with water. Ammonium chloride is another useful byproduct produced by this reaction. Here, acetaldehyde is produced from methyl cyanide. So, methyl cyanide is a nitrile compound. There is an imine intermediate form when the nitrile undergo reduction with stannous chloride and hydrogen chloride gas, that is in ethyl acetate solvent. This imine intermediate is subjected to hydrolysis to yield the corresponding aldehyde. When we examine the mechanism of Stiffen reaction, there are 4 steps involved. First step is gaseous hydrogen chloride is added to the given nitrile, that means cyano compound, which react to its corresponding salt. In the second step, a single electron transfer from stannous chloride reduces this salt. With further reaction with HCl, the following salt is formed. In the third step, the salt obtained in step 2 precipitates shortly after an aldimine tin chloride. Fourth step consists of the hydrolysis of aldimine tin chloride yields an amide. The required aldehyde is formed from this amide. Thus, the required aldehyde is achieved from the nitrile provided. It is important to note that the reaction is more efficient when aromatic nitriles are used instead of using aliphatic nitriles. The reaction is an organic redox reaction. Substitutes can improve. The electron density will improve the formation of aldimine tin chloride. Electron withdrawing substituents also promote the formation of amide chloride. The quenching of the aldimine tin chloride with water yield the amide, from which the aldehyde is formed. The next one is Etard reaction. The oxidation of aromatic methyl group or heterocyclic bound methyl groups to an aldehyde using chromyl chloride is called Etard's reaction. Example, toluene can be oxidized to benzaldehyde. The reaction begins with an alkene allylic hydrogen reaction with chromyl chloride, forming a precipitate called the Etard complex. This Etard complex is then decomposed with the help of a reducing environment to prevent its oxidation into a carboxylic acid. This reducing environment is generally provided by a saturated solution of aqueous sodium sulfite. Carbon tetrachloride is the most commonly used solvent for this method, but carbon disulfide and chloroform can also be used as solvents. Aldehyde product of high purity can be obtained by purifying the Etard complex before its decomposition. Its reaction with the unreacted reagent is prevented. The time frame for this equation may vary from a few days to several weeks, but the yields are relatively high. The reaction mechanism of Etard reaction is an end reaction with chromyl chloride forming a precipitated Etard complex is the first step of this mechanism. The precipitated Etard complex is decomposed by 2,3 sigmatropic rearrangement, a pericyclic reaction where the end result is that one sigma bond is changed to another sigma bond via an uncatalyzed intramolecular process. Reducing conditions provided by saturated aqueous sodium sulfide prevent further oxidation of the Etard complex into a carboxylic acid. Carbon tetrachloride is the most common solvent used in this process. This reaction provides a very easy method for the oxidation of toluene to benzaldehyde, which is utilized to add an almond flavor to foods and some cosmetic products, making it a valuable chemical. However, due to the sigmatropic rearrangement, obtaining aldehyde products from reagents other than toluene may prove difficult. Dear friends, thank you for watching. Don't forget to leave a like and please subscribe my channel.